Homework, project? No? Anything from last time? Anything I need to know? Nothing? All right. So today we're going to keep going on a little dive into machine learning. So last class we were talking about these approaches to decision making, right? And we did the first two, which was basically doing the joint and then using the joint to get the conditional. And we saw like that naive Bayes was one way of doing that. And then we talked about maybe we could directly estimate the conditional. We had that magic function, which was the logistic function. And then we optimized those parameters. So those are called generative versus discriminative models, right? Where we're optimizing the joint versus optimizing the conditional with that magical function that sort of works out so everything's a probability and tries to minimize probability of error. And we saw how that was consistent with the naive Bayes assumptions when we did it that way. So the aim of this class is to look at that last one, this last approach. So what's different about this approach compared to the first two? High level. What does it say that we're trying to do? We're to directly estimate f of x, some function f that takes as input x, my observation, and then outputs y, which is the class. Why is that different from estimating the joint distribution or the conditional distribution? Yeah.
Does it mean for this method we don't try to model the internal mechanism?
Yeah. So we could still try to model the internal mechanisms, but we're not trying to model it as a probability distribution, right? So we're not necessarily going to have probability. Some of these methods that we'll talk about, you can retrofit probabilities to them. So like you can train them on some of your data, and then you can use another subset of your data to like estimate if it says in class 1 and I test it on this sort of validation set, 70% of the time it says the right answer. So that's what I'm going to use as my probability. If you want probabilities for like downstream processing or something like that. But they're not, in their formulation, these methods are not going to directly use probabilities. But just like we said before, you can still, like, so Jane says, right, the rational thing to do is to be doing this probabilistic reasoning. And in fact, like we did those, we've got from these basic first principles, if you just want to try to do something that follows the rules of common sense and you do anything but probabilistic reasoning, you're going to be irrational, right? So does that mean that this is fundamentally like unfounded? Like, does that mean we should just not look at number 3? How can number 3? So I mean, I'll say that number 3, like a lot of these methods are very popular and very powerful. So how can we reconcile that with what Jane says, which is that if you don't use probabilities, you're going to regret it? Yeah. That's right. Yeah. So you can show that using number 3 does the same thing that Jaynes says you should be doing. It does it with different computational mechanisms. Maybe it does it for different reasons. Well, I don't know different reasons, but like the way that your code is structured is going to be different, but the decision making that it's making is going to be consistent with Jaynes, at least some version of that. Of course, whenever you do this, even with these first 2 methods, right, we were making assumptions, independent assumptions about our data that weren't true. And Jane says you're not allowed to do that. If you make assumptions that aren't true, you're going to regret it. Why do we do that anyway? Why do we make those assumptions even if they're not true for number 1 and number 2, for naive Bayes and logistic regression? Yeah. Right, to simplify the computation. So even though sort of theoretically, like the right answer, we could probably get a better answer if we respected more of the assumptions, if our model matched the data with higher fidelity, right? But because it makes computation easier, we play this game where we're like going to pretend things that aren't really true, but then that's going to let our very powerful computers and our machine learning run, and we're going to get answers that are useful today instead of waiting, until the heat death of the universe for us to collect enough data and train these models that are really large. So that trade-off between like sort of doing the right thing and doing the practical thing is has sort of permeated throughout AI. And I think we also saw this in search when we talked about A star and breadth first search, and we compared that to greedy algorithms, which we sacrificed optimality, but often they worked much better in practice, right? Or we saw when we were doing alpha-beta pruning for something like tic-tac-toe, you can go all the way to the root and you can actually get the optimal play. But for a larger game like chess or Go, the space was too big. So even though we might want to do that, we can't. And so we have to do something else. We have to start playing tricks to accommodate for that. And so what you're seeing up here is sort of we've gone through 3 different ways that people are playing different tricks. And we'll go through 2 more today, which is, that fall into number 3, which are support vector machines and decision trees. And I think decision trees are on your project. SVMs aren't, but they're very popular. They're very powerful methods, so I wanted to cover them in lecture at least. OK. So to motivate this, I wanted to sort of, this is a figure from the book. And what it's showing is some data points. This is the other thing, we're covering mostly classification in this class. So classification is like, my y's are discrete. There's 5 different things y could be, and that's all. Or in our examples yesterday, y was binary. It's true or false. You can also do what's called regression, where y is some continuous number and x is some continuous number. In this particular example, and a lot of the same things apply, some things are different. So you can, I leave that as an exercise for the reader to kind of go and see if you're interested in regression. This is one example from regression, though. So you have these points, and it's the same points in both A and B. And there's 2 different fits to the points. Okay, so the fit in A is a line, right? And it looks pretty good, right? And the fit with B is some kind of like 7-degree polynomial hypothesis, right? It also looks pretty good, right? So the error, what's the error, just eyeballing it, on A and B? So I can measure error in regression by saying, well, how far is my predicted value for y? How far is that from the actual value for y? So we're at f of x, or f of x is like in gray, and the actual value for y is the circle on the same axis. So what's the error for A? Eyeballing it. Pretty much 0. What's the error for B? Pretty much 0, yeah, right? So like if I had a point, let me see if my laser is going to work. There. If I had a point like here, where my laser pointer is, from my data, that point, the distance between that point and my line, right, would be the error. So like, actually, let's do that. Like if I have a point about here, and I can move it, I can kind of reflect it onto that graph, the B answer would predict that one a lot better, right? Because it would sort of, it would be closer to that line. OK, so now, which would you guys rather pick, A or B, to model the data? The error is 0 in both of them. A, yeah. Why? Yeah. Yeah, it's simpler. So this is the game, OK? You can pick, so when we're talking about F, and F is just a black box, there's lots and lots and lots of Fs. Okay? There's always Fs that will exactly fit your data. Because you can just have an F that does a lookup, right, and returns your data. And there's algorithms sort of based on that called k-nearest neighbor, where they basically just find the data, if you have a test point, they find the data point that's closest to it, return that class. So you can always have an F that exactly fits your data. And you can have an infinite space of Fs. We could have higher dimensional polynomials. We could just keep going up as long as we wanted and have more and more and more Fs. So we have this intuition there that we want to do the simplest thing, right? And the line is simpler than the polynomial. In what particular way is it simpler? Yeah, so like thinking about how you represent the line versus representing a 7-degree polynomial. How many parameters would you need for a line versus a polynomial, a 7-degree? Yeah, 2 for a line, y equals mx plus b, versus like, I think 7. So that means x to the, it's either 7 or 8, depending on x to the 7th, 6th, 8? Yeah, 8, because you have to do the intercept. So 8 parameters for the 7-degree polynomial, right? So it's simpler in the sense that it requires fewer parameters to do this model. And this idea that we want the simplest model possible is something that underlies a lot of machine learning. And in this instance, both of these models are minimizing the error rate. But now let's try to imagine that we perturb these points a little bit. So now, it's still kind of a line. I don't have a slide for this, but it's still I could draw it, actually. That might be good. There's no chalk. That's bad. Does anybody see any chalk? All right, I won't draw it. So use your imagination. You could draw it at your seats if you wanted. So imagine that you took each of those points on that line, and we just randomly jiggle them up or jiggle them down by a little bit. OK? So now if we did that, what would the error be? 0 or not 0? Not 0, right? OK. And now imagine we did that, and then we tried to fit a 7-degree polynomial. OK? We just jiggled them a little bit. Which way? What would the error be on a 7-degree polynomial? Would it be more or less than the error on our line? Less, yeah. Right. What do you think? Do you still prefer A versus B in that case? Or do you want to go with the 7-degree polynomial? Yeah. So OK. So you're exactly right. The answer is it depends. And in this instance, if we invent some new information, the error is noise in our observations, right? So we're going to assume some kind of Gaussian noise. But what's really going on, we think, is a line, some linear process. Then we want to do the best fit line that we can. We don't want to do a 7-degree polynomial, even though the error is less. The training error is less. You can always have a more complicated model and get the training error to 0. So it's actually a trade-off in many cases. In many cases, you're actually accepting more error in your model on the training set in exchange for what you hope is better generalizability when you actually confront your model with new data. And the answer of what to do when is a very complicated one. It really depends on what you know about the data and the model and sort of the domain. So if you actually think a 7-degree polynomial is going on for some reason, and there's situations where you might, like the underlying physical process looks like that, then this might be a great thing to do. It might be the right thing to do. And the linear model might not be so good. OK. So we're gonna sort of keep pushing on this idea during the lecture. And this is just another example of the same thing. So you can have, this is a 6-degree polynomial versus a sine wave. So here, they're not even linear. Sort of going from linear to polynomials is, in some sense, a similar set of model classes. Here, you can decide whether you want a sine wave or you want a polynomial function to fit. And again, the answer, it's hard to decide from this data with what we know which one is better. It really depends on the domain and what actually you think it looks like. OK. So the trick that we play when we're confronted with this, one of the most common tricks that we play is to make our lives easier. So to prevent this issue of the 7-degree polynomial fits our data perfectly but doesn't generalize very well is called overfitting. Okay? So we've trained our model. We've really got very low training error. But when we try to run on a test set, if it's really a linear model and we ask about a data point close to 0, it's going to be terrible, right? If what's going on underneath is really a linear process. So this is called overfitting. And it's sort of the bane of machine learning, where you've picked the wrong model class. You maybe gave it too much power. And you get great performance on your training set. But then you go try it on your test set, and it sucks. It does really bad. We haven't also really talked about training sets and test sets. Commonly, when you do any of these techniques, what you do with any of these 3 methods is you get a data set. You separate your data into training and test. So you might, depends on how much data you have. You might do 50-50. You might do 90-10. Another common thing you do is something called cross-validation. So you have, let's say you do a 90-10 training test split, which 90 and which 10. So cross-validation says, well, I'm just going to do it 10 times. So everything at some point is going to be my training set, and everything's going to be my test. I'm going to train. So I do it tenfold. It's called tenfold cross-validation. I'll train 10 different models on 10 different training sets and test it on 10 different subsets of my test data to try to simulate what's going to happen when I put this model into the wild and it faces real data. So this is very important whenever you're doing machine learning. If you're reporting results on your training set, you're doing this. You're going to have a really great performance if you give yourself a 7-degree polynomial, but you'll have no idea if you're really in A and you're overfitting and bad things are happening. There's actually a pretty interesting example of this where, who's ever heard of Google flu trends? No? Some people. You're going to say what it is?
It's basically just Google tracked where people were searching for information on the flu.
Yes.
And estimated that was where outbreaks of the flu
Right. Right. So this was a public health tool that Google did based on their search. So everybody's every day, thousands, I don't even know how many times a second, people are typing queries to Google. And they were looking at the ones that were about the flu. I have a fever, I have the flu, I don't know, I have a sore throat. And they used this to predict where flu outbreaks were occurring. And in many cases, this was they showed that they were competitive with doctors' reports. So the CDC does a lot of work to track these outbreaks by talking to hospitals and doctors and stuff like that. But Google was showing that they could get an earlier window into this using machine learning on their search results. So identifying where people were searching for flu terms and then saying this is where we think is going to be an outbreak. And then they would look on the CDC data, which would come in later, and sort of train this model. So they got some really nice results on doing this, and they published the tool. But then about 5 years later, I don't actually remember how many years later, but a few years later, they were tracking it. And it turned out that the world changed. Somehow the query space changed. We don't actually even know what changed. But there were some pretty significant errors. Google was predicting, I think what happened was that they were predicting a big outbreak that then never materialized. And the error that they were predicting was way off the charts from what their training validation had suggested would happen. So they were doing a training and testing split, but what happened is the underlying model changed. And so even though their old training data said this was a pretty good model, after a while it stopped being a good model. And it's one of those almost ethical questions about AI because the researchers who did this spent a long time making a really good model, and then they stopped working on it, and they just put it out there and said, whoever wants it, use it at your own risk. And people did use it, and there was concerns about it that it suddenly stopped reflecting reality. Okay, so what we do to try to both avoid overfitting and also to make our training process easier is we restrict the space of functions that we're talking about. Okay, so instead of searching over all possible functions and you get to you can think of a function maybe as a space of all possible programs you could write that take as input x and output a y. All the possible programs, right? An infinite number of possible programs. That space is humongous, right? And if you let yourself search in that space in a naive way, you're going to get overfitting, or you might not even get anything good because the space is so big that it's all going to be terrible. So the games that we were playing with number 1 and number 2 was restricting our space of possible functions. We were restricting it in a particular way by saying, well, these are the parameters of our model, and we're going to estimate these parameters in a maximum likelihood way. And in naive Bayes, we actually got down to, we don't even have to search. We can just run this computation on our data, which was this weighted average, to get the model parameters. We could actually compute our means and our sigmas and come up with the answer. What do we have to do for logistic regression to do that search, to find our parameters? We mentioned it, I think I mentioned it very briefly at the end. So remember we had that funny sigmoid function that was the 1 over 1 plus e to the mumble weighted sum of your features. And we were trying to find our feature weights, right? So how do we get those feature weights? How do you think you might get them if you don't remember? Yeah. What's that? Yeah, gradient descent. So it turns out that for naive Bayes, there was a nice analytic way to get it, which means that there was some function where we just added some stuff up about our training data and divided, and we got our parameters. For logistic regression, there is no analytic expression. It involves integrals that you can't compute analytically. So instead what you do is you do gradient descent. And it does turn out, which is nice, is that the gradient space is unimodal, convex. So when you do gradient descent, you can get to the global maximum of your parameters and do pretty well. And so it's again, because it's convex, you're not searching in the space of all possible programs. You're just walking up the hill. You're doing some version of hill climbing. And you're guaranteed to get to the global optimum. So in this other space, in 3, the general approach we're going to take is by looking at different subclasses, subspaces of functions. And we'll talk about 2 different ones with SVMs and decision trees that have properties that enable us to search them quickly. And then we'll be trying to optimize the performance of the model, usually with some kind of penalty term to prevent it from overfitting. So we want there to be good performance, but few parameters. And that's sort of the game that we try to play. So this is, I've flashed this a couple of times. But this is sort of one very general class of functions. It's called a linear model. So you have some function g of x that equals these weights, w sub t, it's just a transpose to make it dot product with the features that I have. So like in our previous lecture, we just assumed that x was already featureized. Here this is just saying like x could be your raw image, and you got to run some magic programs to extract the features. We talked about that last time. Plus the bias term, so somebody was asking about that. Kind of like a prior, which class, without doing anything, which class is more likely? And then you can actually get to this function by saying if f of x, if g of x is greater than 0, return 1, else return minus 1. So f of x equals the sine of g of x. So what do you guys think about that? How do we pick our weights? What are some different ways you might think to pick the weights? What might you try to do? Yeah.
How about still use gradient descent?
Yeah, that's good. So you can try to minimize your error on the test set. Good. Is that the only thing you could do? So I think what's next is a picture. So this is a 2-dimensional version of this problem where there's 2 features, and the circles, the unfilled circles and the solid circles are the different classes. And we can just sort of imagine each set of the weights corresponds to a line through the space in this linear model. And when you're on one side of the line, the sign thing says if you're on one side of the line, you pick class 1, the other side of the line, you pick class 2. So let's say this is all of my data, and I want to minimize the error.
Distance between nodes of one certain color.
Yeah.
Line.
Yeah. Right. Right. So yes. So in some sense, I could pick this one, and I'm doing perfectly, right? But what makes you worried about? Yeah, like what if I get one that's just a smidge over? I'm going to make a misclassification error. So why do you like this one better? Like you basically have it, right? You want to be far away. You want to be far away from the boundaries, as far away as possible. So this is called maximizing the margin. Okay, I want to have a big margin when I make my classification decision. I want to be as far away as possible from all of these decision boundaries. So you could sort of, there we go. So you can sort of imagine something like this, okay, where I figure out, like I'd search in the space of all the lines that I could draw and identify, so these ones here are the ones that are closest to my solid line, which is the decision boundary. And I want to pick the decision boundary that maximizes this distance of the closest ones. Okay? So that's basically what SVMs are trying to do. This is the criteria by which we create support vector machines. And one of the annoying things about machine learning is they use fancy names for things when I feel like it sometimes overcomplicates the world. So they want to do max margin to find a linear decision boundary. And so they call, I don't know why, but they call these points here, 1, 2, 3. There's not always 3. They call these support vectors. You can kind of think of it like they're supporting the boundary, right? So you're kind of trying to find these ones and minimize this distance as you do this optimization. Okay? So SVMs, they are doing this linear function, and they're trying to maximize this linear thing here. And they're trying to find weights that maximize the margin, max margin. Yes?
For Boolean classification, is it correct to say that the boundary should be chosen right in the middle of two sections, if they're partitionable?
Well, the answer is, again, it depends. So maximizing the margin, why is maximizing the margin nice? We kind of said, right? Like you're going to try to the extent possible to be far away from the decision boundaries, so that if there's new data that's a little bit outside of the data you've observed, you're going to still be okay. What is logistic regression going to do? On this, because I could run logistic regression on the same data. I could maximize my conditional likelihood. How's that going to be different? Intuitively. Is it going to maximize the margin? Is logistic regression going to maximize the margin? You said no. Yeah, you're right. It won't. It's going to do something else. So logistic, what's it going to do? We said it before, right? You can go back and see this picture. We're going to estimate P of y sub k given x. We're going to maximize that term. So what's that called? P of y given x over all of our data. What's that? The probability of, yeah, you're right, it's a probability. So it's a probability of what? We called it, so the first one we called the joint. What's the second one? What's that? What's that? Likelihood, yeah, that's right. The word likelihood is in it. So the first one we call the data likelihood, the joint likelihood. Okay. The second one is also likelihood over the data likelihood, right? Because remember we had that sum over all the data points. What's that?
Some number.
No, it's not a number. It's a word. It begins with C. Conditional. Yeah. The conditional likelihood. So we're going to maximize the conditional likelihood over all the data. Okay? So SVMs are going to find these points that are close to the decision boundary and basically only use these support vectors to pick the exact slope of that line. Okay? When we maximize the conditional likelihood, we're summing out over all the data points. So we're going to use all those other points too to make our fit. Okay? So sort of intuitively, it's going to like try to give you a better picture of what the data looks like. Logistic regression is going to do that. It's going to use all the data points when it comes up with those feature weights. Whereas SVMs are just going to identify the ones that are closest to the margin, and that's how it's going to decide. It's going to try to just give you the biggest distance between classification accuracies, support vectors. This is what the math of that optimization actually looks like. So I think I have a legend over here. So like W is the weights, B is that bias term, so it says which class is a priori, without even looking at any data, which class is better. And then we're minimizing over all of our training points this distance. So this is the weights times the features. That's like a dot product that basically measures the distance. The t to the n makes this, like, it has to be -1 or 1 for SVMs. And that makes it work out that it reflects the class in the right way. And then W is the regularization term. It says I don't want to have big weights. I want them to be small. Again, to prevent overfitting. And then we're argmaxing over W and B. So that's the sort of math of max margin. It turns out that just like in, so optimizing this directly is hard. You're still searching in a pretty big space, but there's a trick that you can play just like in logistic regression, it turned out it was convex, so you can play a trick to walk up the convexness. There's a trick you can play involving Lagrangians, which I don't want to actually go through in the full detail. I just want you to know that there is a trick and kind of how it works without going to the full model, but basically converts it to a quadratic program that you can optimize efficiently. And it's gradient descent kind of process with some constraints. So like subject to some things about the weights and stuff. So you can solve, and like whenever people implement SVNs, usually they use some quadratic program solver, or you can just directly use an SVN library and find the weights that do this match margin thing. And if you're interested, there's some, you can go read about Lagrange multipliers and see how it actually all falls out. But we're going to kind of gloss over it, just like we glossed over the optimization in logistic regression. Although you guys are going to do it when you're in your project. Okay. So here's an example of this on some real data. I guess the other example was from the book. This example is from Python programs that I can upload. So here it's basically picking these SVMs. And what I'm going to do is overlay that with a logistic regression fit to the same data with the same features. So you can kind of see. It turns out that here logistic regression is a little bit better on a test set. But you can kind of see how the SVM is doing this margin thing, but the logistic regression is sort of tilted over to kind of fit these points over here, right? It's doing this better data fit. And it's not like one is better than the other. Sometimes one is better, sometimes the other one is better. Sometimes the most important thing that you care about is like you think that there's this overlap and you really just want classification accuracy, and so SVMs are a pretty good out-of-the-box thing to use. Sometimes you actually want, so what does logistic regression give you, besides linear decision boundary, which you can see both of them give you, what does logistic regression give you that SVMs don't? If I have a logistic regression model, what do I have that SVM wouldn't give me if I just had these weights? Yeah, I can get probabilities, right? So if I get a new training example, SVM is going to say thumbs up or thumbs down, and that's it. And hopefully it does the right thing, right? Logistic regression is going to give you a number between 0 and 1, a probability that it's in, if you think of it of a binary thing, it's going to give you the probability that we're in class 1. And if that number is close to a half, let's say it's like 52%, you might say class 1, but like it's going to tell you that it's unsure. So sometimes you want to know that. Sometimes you want to make decisions based on that, or you want to collect more data, or you want to reflect that to the user. You can get something like that from SVMs too. How might you do that? We talked about it a little bit at the beginning. How might I get a probability of correctness from an SVM? Yeah. Yeah, I could look and see how close I am to the decision boundary. So that would give me a distance, and then maybe I could coerce that to a probability. I could normalize it or something. And people do things like that. What else could I do?
Close the service to existing points. Instead of being close to the boundary, closer to the existing points of a certain class. So if you're like an outlier, but
Yeah.
in the same boundary, you're still assigning a low weight to that point.
I didn't follow it. So you're,
So
yeah.
we would prefer points which happen to be around the cluster of points
Yeah.
in a certain class.
I see. Sample nearby points,
Exactly.
and then
So
say, yeah,
you have an outlier,
yeah,
which
yeah. I see. So if you're like, let's say that you're right here, the 3 closest points are going to be red, red, and green, right? And then look at that. Yeah. And that actually leads to a new classification algorithm, which we're not going to talk about in detail, called KNN, K nearest neighbors, that looks at the 3 closest points and then returns the answer. And it's nice because it's just directly using your data in a very direct way. What might be nicer about KNN than SVMs? I think my next picture kind of gets at that. So what's going to happen with this, with an SVM, with a linear SVM? It's going to be a disaster, right? It's going to try to draw a line. I think that's the line it actually does draw. And it's going to suck. What might KNN do? Do better? Probably much better. Yeah, right. On the other hand, what if you have very few data points? SVM might give you more power out of that if it really is a linear boundary. It might be the right thing to use. OK. So this is a disaster with a linear SVM. And we could use something like KNN. And actually, I should say at this point, maybe, there's lots of libraries out there that do all this stuff. So one of the best ones is in Java. It's called Weka. And it's got like 50 different algorithms. One of the focus areas of machine learning research is like coming up with new and better algorithms in this space. And a lot of them are implemented in Java. There's another one in Python called, so I use scikit-learn in Python to make these. And there's many others out there. There's a lot. We ask you to implement it because you get a sense for, especially some of these sort of foundational ones, so you get a sense of what it's really like to implement it. But for a lot of practical applications, like in our research, for example, we usually don't implement them. We usually use something out of a toolbox. OK, so what do we do about this? We could use KNNs. We could use a different model. Is there a way we could make SVNs work? What's logistic regression going to do? Are we going to be happy or sad? Sad, yeah, same thing. It's linear decision boundary. There's really no good one. And yet, look at our data. Look at how beautiful it looks, right? Like there's this is generated by drawing that circle and sampling. And if you're inside the circle, you're positive, and you're outside the circle, you're negative. It's an artificial data set. But you can imagine lots of instances where it's real, where data would really look like this, as close to something in a circular pattern. So how can we fix this problem? Yeah. 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 So right. So we can somehow transform our data into a different space, and then maybe it's going to be linear in that new space. And in fact, that's a very common thing to do. It's called, so people call, who's heard of kernels? Some of you, yeah. So this is this idea that I'm going to use some transformation to go from this space to a different space. That transformation is called a kernel. And the reason that we do it is if we stayed in this space and we tried to find a linear decision boundary, we would be very, very sad. But we can go to a new space, and in that new space, we can find a linear decision boundary, and it's going to work really, really well. So we'll go through an example of that. All right. So this is a new feature space that's designed specifically for this example by knowing about what this thing looks like. And it basically converts it. Usually you're adding a dimension. OK? So it converts it into this cone. OK? And actually, I can run it. You can see a 3D version of it. We'll see if that works. Let's see, L3. My computer's being really slow. There we go. So this is just a like an interactive 3D view of this guy, so we can kind of drag it around. So what do you think about an SVM in this space, this 3D space? Yeah? Yeah, it's going to be a plane in the 3D space. It's not going to be a line. It's going to be a plane. When people talk about hyperplanes, they just mean like a line, a plane, n-dimensional planes. And as we get more and more features, we're not going to be in 2D or 3D spaces. It's going to be n-dimensional spaces, but it's still going to be a linear decision boundary. It's going to be a hyperplane. So in this 2D space, we couldn't come up with a good linear decision boundary. But in the 3D space, I think it's easier to see the 3D when you can move it, which is why I'm running it like this. You can kind of see where the plane's going to go to make the boundary. Yes? Okay. All right. And the way that we came up with this is we thought really hard. Or we designed a problem intentionally. This idea of the problem is from the book, using the circle and then the new feature space, where it kind of works out that it goes into a linear boundary. And it's typical that when you do this, you go to more dimensions, because it kind of spreads things out so that you can come up with a linear boundary. And then the same optimization as before. So it's still a linear classifier. You're still doing this quadratic thing with Lagrangians and stuff, but you did this kernel trick. And there's actually one more nice thing about it. So it turns out that when you do this Lagrangian optimization, you don't actually need to look at your data directly. So this thing here is the dot product of two of your data points. To do the optimization, you can just treat it as an arbitrary function of those two data points. So you don't actually need to compute your entire feature vector as long as you can compute the dot product efficiently. So that can make things go a lot faster, because you can basically, you don't need to spool out the entire features. And that's why that's where the K there is the kernel. So when people talk about different kernels, I think, there we go. So the kernel for this, so one way to do it is to sort of project into this space and then train a linear boundary in this new space. But you can also just tell the SVM, look, this is the kernel I want. It's going to take x, m, and xn, and it's going to multiply them and square them together. And then you can do the same training process without actually converting all of your features into that new space. So it goes faster. And there's lots and lots and lots of kernels. This is another area of active research in machine learning, is finding new kernels for new types of data. So linear, polynomial, radial basis functions, which is how far you are from different key points, sigmoid. And these all introduce different types of nonlinearities into the model. So the linear classifier, so here the linear classifier doesn't work, but when you introduce a kernel function in this way, we can go back to having a linear classifier work. So there's different ways of introducing nonlinearity. And the one that you pick depends on your data and your domain. There's some recent papers that do this with parsing, and they use parse tree kernels to reflect the structure of natural language when they do things. So that's sort of the, and actually it turns out you can use, I thought I had a picture of this. Maybe I didn't. I thought I had a picture, but maybe I don't. You can use this trick with logistic regression too, right? But to do it with logistic regression, I got to do this. I got to actually convert it to the new feature space and then run it on that space, and then it's going to be happier, right? With SVMs, because I have the kernel trick, I don't actually have to convert all my data points. So that's an advantage of SVMs. There's this computational speed up that you can get. So are there any questions so far about any of that? Yeah.
Under what circumstances does SVM come up with a more accurate classification than logistic regression?
Yeah.
As far as I understood, logistic regression takes into account all points.
Yeah.
But
so
it only takes into account the closest point.
So the answer is that they're both pretty good. There's often not a lot of difference between the two approaches. In a situation where...
But why not?
Why not?
Why isn't there a significant change?
Why isn't there
a limited number of points?
Right. So if you think that logistic regression, the features that you're using, are accurately representing the data, and that all the data points are telling you something, then logistic regression can be a good choice. If it's the case that a lot of your data points are let's say that you're in a situation where there's a really large amount of diversity in your data points. So an example might even be this one. So the circular example here, where all the ones that are close to the circle, a certain feature, a family of features lights up. But when you start to get far away from the circle, all kinds of crazy things happen. You might see you know, like maybe, like I'm kind of making up an example here, but like, you know, if I go over in this corner, maybe my feature, like if you imagine this is like a robot trying to figure out if it's in a certain location, and I go over in this corner and I'm in the bedroom and my bed detector lights up, and I go over and up in that corner up there and I'm in the laundry room and my washing machine detector lights up. Logistic regression is going to try to account for all of that variation. It's sensitive to the amount of data that you've got. So if you don't have, so in the situation where you don't have a lot of data to train on, it's still going to try to account for the noise that for that diversity, but you might not have enough data to fit. Whereas SVMs are going to be like, oh, the only things that really matter are that like my decision boundary is like right here, and the only things that really matter is that I'm in the what did I say, bedroom and laundry room, that I'm in the kitchen, and the microwave detector is on. It's going to like look right at those margin points and give you a really good boundary. Whereas logistic regression, that tilt to the line, if we go back here, is going to depend on all these points. And if I don't have enough points to give it a good tilt, it might do the wrong thing. If I have lots and lots of points and good features, it might do better because I'm tilting the line in a way that reflects the true underlying distribution, especially as I add more trained data that I haven't seen before.
And also you have lots and lots of points,
Mm-hmm.
but you have like outliers,
Mm-hmm.
then logistic regression would perform horribly because it's also
Yeah. Well, it's sort of this trade-off, like depending on how big your feature set is, lots and lots of points. Like it depends on how many features you've got and what your data looks like. So like if you have enough points, logistic regression might do pretty well. But when you start to have fewer points, SVMs are going to be sort of like, I'm just going to try to maximize my margin, get the best boundary I can, and who cares about all these other points up there and down there? They're far away. I'm not going to even put them into my model. People use both for different applications. A big thing that some of these data considerations are go into it. Also, whether you want the probabilities or not goes into it. But it's like for computational linguistics types tasks, both are very popular models. Naive Bayes is less popular, even though you guys are using it for spam filtering. Does anybody want to guess why it might be less popular? Too easy? Well, I don't. I mean, we want to use the simplest thing that works, right? Like that's a design consideration when you were putting these things together. Yeah. So it's really making a strong conditional independence assumption about the data. And what effect is that going to have about your features? So what is that going to mean about the probabilities that you get out from naive Bayes? So like, let's say that I have features, and I'm assuming they're conditionally independent, but they're really not. So I have these two features, and they're both correlated with each other, even given the class they're correlated. But I'm assuming they're not correlated, and they both strongly indicate that I'm in class 1. What's naive Bayes going to do with that? When it computes those feature weights, what's it going to do? Yeah, they're both going to have big weights. And so when you sum everything all up and multiply it all out, what's that going to do? Let's say that they're both positively associated with that class. So you have these two things with big weights. What's your overall probability going to do? Yeah, you're going to overestimate. So what naive Bayes tends to do, it tends to be pretty accurate, but it tends to overestimate or underestimate your probabilities. You'll get probabilities very close to 0 or very close to 1 when you have these correlated features, and it's just independently, it's basically assuming they're independent. So all of the signal from one, so really what's happening, there's no chalk yet. Really what's happening is like something's happening that's turning on these two features that you can't really observe, and you're assuming that they're just totally independent. So each feature independently gives you a signal that you're in class 1. But really, there's some amount that's overlapped of these two features. If you draw a Venn diagram of the signal, there's some amount that's overlapped. Naive Bayes is going to count it twice. And that's going to bump up or bump down your probabilities. Logistic regression, when you're optimizing the conditional likelihood, will not do that. So it turns out that this is like a little detail about logistic regression. The feature, I said that there's a global optimum. There is not a unique set of feature weights at that global optimum. The feature weights, and it's basically because of this issue, right? The feature weights, when you have these two correlated features, you could bump up the weight of one and bump down the weight of the other one. And the model would do the same thing, if you can kind of imagine that. Like it's going to, you know, you're sort of free to pick where, which, if these two correlated features, you're free to pick where you put the weight on one versus the other. But it'll sort of do the right thing of not double counting them by maximizing the conditional likelihood. So that's sort of why people sometimes avoid naive Bayes, because of this overestimation error. If you want probabilities, you want good probabilities, logistic regression is a good thing to use. Especially when you think you have, if you think you have not conditionally independent features, which is actually quite common, that you don't.
Quick question.
Yeah. Yeah.
So is the logistic regression, the function is mathematically similar with in naive Bayes?
Yes.
Is it exactly the same or is it different?
So the parametric form for the logistic regression function is what you get for Gaussian naive Bayes. When you use that same model and compute the conditional likelihood of that model.
But the question is, if they are mathematically the same, why naive Bayes is making assumptions?
Yeah, it's because of the way that we're estimating the parameters. So I could throw up the slides from last time, but maybe I will. That's the best way to answer it. Let's see. Here we go. So this is the derivation of that relation, if you remember from last time. So what we did is we did this algebra, and we got to this parametric form where we could plug in the parameters for naive Bayes, which we computed in the same, like the analytic way. But I am free to replace these with W's. Okay, I think I have that maybe over here, and optimize them in some other way. And I will get, in general, well, it sort of depends, right? If my naive Bayes assumptions are true and I'm the limit of infinite data, then I will get the same values. If I just directly optimize these W's, I'll get the same values as this in the limit of infinite data, and the model is true. They really are conditionally independent, given the class. When the model is false, when they are not conditionally independent, given the class, logistic regression will do something different from naive Bayes when you optimize these W's directly. Okay? So then you could sort of imagine, like you could plug in your naive Bayes weights into this formula if you wanted to. It would be the same thing as doing naive Bayes directly. Like you're somehow getting the conditional likelihood. It's the exact same thing. This is sort of a proof of that. But the weights that you get when you optimize it directly will not be the same. They'll be different. And then we had this pattern up here, right, of how they tend to be different. Okay? Cool. All right. So we sort of, and there's actually a very close relationship between logistic regression and SVMs, and we're both linear models. And you can sort of think about that kernel, the exponential sigmoid thing as a kind of a kernel function. But then you optimize different things about the models. So they're kind of working for the same reasons. So now we're going to talk about something that might be very, very different. Before we do, I guess I want to ask you guys, so we're going to talk about decision trees, maybe. But I want to ask you guys, let's see, decision trees. Where basically you have this tree of if statements. So I want to ask you guys to take a few minutes at your seats and talk to somebody next to you. We've talked about linear models, we've talked about decision trees, or we've just thrown up decision trees. Think about a few other model classes that you might use, you might heard of, classes of different functions that you could use to train data. And then we'll come back and talk about them. Take a couple minutes to do that. So like 15 more seconds. All right, when we finish up? Finish up. So who wants to share with the class what you thought of to do this? So like if you imagine writing a little Python, like these Fs are the space of all programs. So we can imagine a little Python program for logistic regression, where I've got these feature weights, and it's going to be something like math.exp 1 over math.exp, and then maybe I'll have a for loop to do a sum and return the probability. Or maybe I do that, and I wrap that, and I do if it's greater than something, return true, otherwise return false. Or for an SVM, it's going to be something like, it's going to be something along the same lines, and but it's going to be linear instead of the exp thing, and I'm going to do that. Decision trees, we haven't talked about them very much yet. It's going to be like a bunch of if statements, right? If this, and that, then that. If this, if this, if this, if this, return true, else return false. Okay? It's a space of all possible if statements, given your feature space. So what else could we do? What else is out there? I heard you guys talking. There had to be something, right? Yeah?
So first we come out the criteria to compare two data points is similar.
Mm-hmm.
So we store all the training data points, and
Yep.
when we get a new data point, we compare it with all the things in the
Yeah. Right. So something like,
post the signal.
so for each point in, or maybe, I don't know, we'll say like argmin def x dist x d for d in data. I'm going to go up. For d in data, x star, return what? Yeah, label x star, right? So that's like one nearest neighbor. Find the closest point, return the class. What else? What else could you do? Is that it? Are we done? Yeah. A KD tree. So what would that look like?
So basically, like, if something like this accepts,
Yeah.
for example, the reverse criteria of patrons, instead of returning like, three values, just return membership value.
The which?
Membership value, like some kind of a number between 0 and 1. You can always come back to that criteria after you
Uh-huh.
choose numbers.
Yeah, so like somehow get like an estimate from each feature and then linearly combine them in some way. Yeah, so people do that. They call that like ensemble learning. What you do is you train lots of really shallow classifiers on subsets of the features. And then they somehow combine them together and get an overall class. Okay? So people talk about boosted decision trees. It's another version of that, where you train a regular decision tree, but you train lots of them on subsets of the data. And it's a way to prevent overfitting. So that's good. Any more? Should we go on? So decision trees are kind of like this if statement thing, right? Like we're going to somehow, our program space, our function space is going to be this tree of all the different possible if statements I could have. And this is like a flowchart version of that, so I'll bring this back down. This is a flowchart version of that. So like this is from the book. It's trying to estimate, if I go into a restaurant, should I wait at the restaurant for a table or should I go on to the next restaurant? Yes or no? And so the first thing, this is an example of a tree that you might use to do that. So the first thing is whether or not there's any patrons. If there's no patrons, then you go away, because it's not a good restaurant. If there's some patrons, then you stay, because it can't be that bad and you don't have to wait. If it's full, then you see, well, how long is the wait? If it's really long, I don't want to wait that. If it's more than 60 minutes, I leave. If it's between 30 and 60, I check out if there's an alternate and try to figure it out. If it's a Friday and Saturday, my alternate's probably going to be full too, so you sort of decide. If you're hungry, then you switch. If it's raining, you don't want to go outside, right? So these are all different features that might weigh into your decision. So the function for what the classification decision looks like is this pile of if statements. So how could we learn that function? For decision trees, you're going to implement something like this. You're gonna look at a bunch of training data, right? And you're somehow gonna write a program like this. How can we do that?
You mean in Python? Like
Yeah, let's imagine this in Python.
bunch of if statements,
Bunch of if statements, yeah. So, but how do I know which if statements?
your features. So each box is a feature.
Yeah, so each one is a feature. But I could decide which order to do it in, right? So I could decide to switch on whether or not it's raining first instead of patrons first. Okay, depending on that, I will get different answers at the end. So how do I decide what to switch on in which order? What am I trying to do? Yeah.
You take off the most powerful feature.
Yeah, right. So you can imagine, so you're kind of getting towards some kind of algorithm for saying, well, this is a pretty good feature to start with. So I'll split on this feature first. And then if I have some kind of weighting thing that says these are good features and these are bad features, it suggests a kind of greedy thing where I'm going to do this feature and then this feature and this feature. And then what do you do with the leaf nodes when you run out of features? What does your program do? Gives back the answer. Which answer? How do I decide?
They said you would be there.
Well, I've got all the way down into this leaf node. So how do I decide whether, like, way down at that leaf node, the answer should be yes?
I mean, I guess you got to that leaf node only based on your previous decisions, right? So don't you already know?
Yeah. So when you evaluate, like, the output of this algorithm is when you get all the way down to the leaf node, you want to say yes or no. This is in this class or in some other class, right? But when you're training, you're coming up with, like, so we imagined we've got some kind of thing of saying these are good features and these are bad features. So we're going to split on these features. Once you know the feature, and let's assume discrete case for now, you have to split on those discrete values. So you're going to have subtrees for each one. And then you do the next feature. So you get all the way down to the leaf nodes. So that's good, right? You've got a lot of if statements and stuff. But now you have to return something. How do you decide what to return? Because if I don't return anything, I'm not. Why did I do it, right? Like, I have to return something. Maybe, yeah.
Make each decision and find the utility based upon it.
How can you find the utility? Yeah, you're right. But how can we do that?
There's like a goal test or what?
Yeah, where do I get that from, though, when I'm doing this?
Look at the subset.
Yeah, I look at my training data. So yes, I estimate the utility of saying yes versus no on my training data. And that's where I get my answer from. And when I'm picking out which splits are good, what do I kind of want to have be the case with these leaf nodes? So each of these leaf nodes has a pile of training data associated with it, right? Right. So it's like all the training data, let's say over here, had full patrons and a greater than 60-minute wait. And there's a pile of the training data that is in that leaf. So what do I want those leaves to look like for a good tree?
In fact, we have two classes. One's the results of so we have partitioned the data set to two parts. And
Yeah.
I want one part has
Yeah.
a lot of yes.
Yeah.
With fewer no.
Yeah.
And another one has
Yeah. Right. Right. So does that make sense to everybody? What he's saying is you want the data to be like separated. You want these leaf nodes to be mostly one class. What would be bad if we had, let's say it wasn't that way. What would it look like instead? Random. And then what would you say for the class? Flip a coin. Yeah, it wouldn't be very good. So going back to our idea, we're going to pick the good things to split on. The way that we're going to decide what to split on is the ones that are going to give us relatively uniform decisions at the leaf nodes. Okay? So there's something else you have to think about when you're doing this. Does anybody, it kind of relates to what we talked about at the beginning of class. Anybody want to guess what it is or think they know what it is? What if we did that? Is the answer unique if we do that? Are there multiple different trees we could have? There could be multiple different trees. So what do we want to be true about our tree? Besides having minimum error on our training set. What's that? Yeah. What do we want to be true about our tree? So what would happen if we had like a really, really big tree?
Maybe balanced trees.
What's that?
Maybe balanced trees so that on one side you
Yeah.
can have like a deep.
Uh-huh. Yeah, you're kind of getting at it. But let's imagine you had a really, really big tree versus a really, really small tree. So what might be true about the really, really big tree? Yeah.
It might be slightly more accurate, but it needs to be
Well, typically when you go down these trees, it isn't actually that long. Computers are fast, right? So you're just like, assuming you already have the features, computers are fast. So going down the tree typically doesn't take very long. In the back? Yeah. Yeah. That's right. That's right. So you might be overfitting. If you have a really, really big tree that like you're back to that 7-degree polynomial case, right? Where you're basically memorizing your train data, but it really might not generalize well to your test set. Versus a smaller tree, you might have more training error, but you also might generalize well. So it sort of comes back to that training overfitting issue. Whoever was saying that like the time to get down the tree, it's actually another advantage of decision trees. If you don't need to, you don't have to compute all your features. So in a lot of applications, a lot of these algorithms just assume I'm going to give you all my features no matter what, and then I'm going to do an SVM or a logistic regression. It's just going to go. In a decision tree, I can compute my features on an as-needed basis, and if there's ones that are expensive to compute, I might not have to compute them. So typically, the time to go down the tree, if I have all my features, is pretty negligible. I'm usually talking about like 100 features or less. Even if it's 1,000 features, computers are fast. Like it'll go fast to get down to the tree if I've got my feature values. But computing those features, I mean, you guys remember from last time we were talking about like computer vision algorithms, and there might be themselves calling complicated machine learning things, and maybe I'm looking stuff up on the internet. Maybe I'm going to Amazon Mechanical Turk for some of my features. Computing those features could take a really long time. So that is another reason I might want a tree of a particular shape. To try to get to like I might know that I have this feature, it's really good, but it's really expensive. And if I can avoid it, then I want my tree to kind of reflect that. Cool. So basically, the training algorithm people use, this is it. But like it has this, it's recursive, and it just calls this importance thing that essentially does, so this idea that we want things to be uniform. We want there to be low entropy at the leaf nodes. So it's basically a greedy algorithm that's splitting in order to get a low entropy down at the leaf nodes. And then like at the leaf nodes, you pick the one that has the most stuff. And then you have this pile of if statements for your algorithm. Yes?
What is plurality value?
Plurality value. It's telling you, so basically it's voting to tell you what class you're in. So the one, this is for like not binary but multiple classes. So it's saying return at the leaf node, return the answer that has the most votes at that leaf node. of the examples at that leaf node from my training data. Yeah, examples is the stuff at that node from the training set. So that's sort of the training algorithm. Here it says, breaking ties randomly. All right. So that's sort of this is like machine learning in 2 lectures. But we kind of went through, so we said naive Bayes maximizes the joint data likelihood. Logistic regression maximizes the conditional likelihood. SVMs maximize the margin of the decision boundary. These are all, they're doing all those, like they're doing that. Like the math says that's what you're going to do. Decision trees don't. Like you're not guaranteed to find the optimal tree with this algorithm. It's a greedy algorithm and it might not find the optimal tree. But generally it does pretty well. And it searches for small trees with low classification error. And as we've alluded to, like we talked a little bit about KNN, and there's lots, and ensemble learning, there's lots and lots and lots of other approaches. And if you think this is cool, I recommend taking Eric Sutter's machine learning class. And you go into the gory details far more than we will about all of these different algorithms for classification. But this is just giving you a taste, because we use it a lot in AI, and we'll sort of see how this sort of individual decision making, which is what we're talking about in this section, can extend to making sequences of decisions, which is what we want our AI agent to do. So we're going to finish a little early. So if you have any questions, I'll take them. Otherwise, have a good weekend. Hey.
Between a generative and a descriptive model.
So it's basically what